Okay, so I think most of you guys probably already know me, but for those who don't, I'm Ben. I'm a junior in the math department here, and this talk will be on the classification theorem for finite simple groups. So first, I'm going to explain briefly sort of what a good classification result should do. We oftentimes have like some large collection of objects that we're interested in studying, and we would like to understand it in a more minimal way. We have some notion of sameness associated with certain objects, which we call isomorphism. And when we say two things are isomorphic, we mean they're the same in some suitable sense, corresponding to whatever objects we're working with. So a classification of a certain collection of objects should be a subcollection of those objects such that every object in our large collection is isomorphic to exactly one object in the small collection. So it sort of has all the information we need up to isomorphism, and there's no redundancy. So we have a unique object in this classification collection. So I'll give an example from linear algebra to illustrate this. So I'll call this the classification for matrices over an algebraically closed field. Okay, so this is a strange way to write this. What this is of course just the Jordan form. So if you remember from linear algebra, okay, what is the Jordan canonical form? Well, you give me any matrix over an algebraically closed field. Let's call it A. And I know that A is going to be similar to some matrix J, and J is going to be some block diagonal matrix with blocks J1 down through Jn. Zeros everywhere else, right? And we have this additional condition that these blocks should have a certain structure. So they should have some value lambda I on the diagonal and ones on the like super diagonal, the one directly above it. So this is the existence part of the theorem. It says, okay, you give me any matrix, I can find some form matrix that it's similar to. And then we also have a uniqueness statement that tells us that, okay, if A is similar to some matrix J of this form, this is the only matrix of this form that it can be similar to, up to permuting the order that these blocks appear on the diagonal. If I permute these blocks, no matter how I permute them, A will always remain similar to that, but we can sort of identify those block permuted matrices. And maybe a more precise way to do this is we can define block A will just be, let's say, the multi-set of all Jordan blocks that show up in this decomposition, and then we don't have to worry about any sort of permutation issues. So two matrices will be similar just in case they have this same block decomposition in like multi-set equality. Okay, and so the reason that this might be called a classification theorem is because we know that A is similar to exactly one matrix of this Jordan form, right? And this similarity that we write here, this is the correct notion of isomorphism for matrices in this sense, right? And the same sort of thing can be regarded as like a classification for linear transformations on a finite dimensional vector space over an algebraically closed field. So this is sort of our starting result. And now I'm going to prove a cool little theorem which uses this result, at least to give an easy proof, and hopefully we'll be able to use this to sort of build a more general idea of how we should attack this classification of finite simple groups. So theorem, I guess, if it can be called a theorem, maybe a lemma. A is similar to A transpose for any matrix A, square matrix A over a field K, any field we want. No algebraically closed assumption needed, although for the purpose of this talk, we will assume it's algebraically closed because we'll need something stronger called the rational canonical form to deal with the general case. But we can prove it super easily with an algebraically closed field just with the Jordan form. So, okay, proof. We know that A is similar to J, where we'll just take J to be the same sort of thing as before, our Jordan matrix. And we can then define a matrix let's say B sub I. And this will be something that kind of looks like the identity matrix, except it has its ones running along the off diagonal instead of the main diagonal. And I call it B sub I because this B sub I should correspond in size to the block J sub I. So we want to be able to have them have the same size so we can multiply them together. And what we can then observe is B sub I, J sub I, B sub I inverse is just equal to J sub I transpose. B sub I inverse is actually just B sub I, again, you just multiply them together, it's the identity. And this is just like an elementary verification. And so with this in hand, we can define, let's say, B star, and this guy will be the block diagonal matrix with blocks B1 down through Bn. Okay, and another sort of easy verification will tell us that, okay, B star J, B star inverse is actually equal to J transpose. Okay, this is just multiplying block matrices, and then we're done because A is similar to J, and we just demonstrated that J is similar to J transpose, which is of course similar to A transpose, because we know A is similar to J, so take transposes, and we get this guy. And for A is similar to A transpose, right? So Jordan form makes this really easy. I challenge you guys to find a really easy proof of this fact without using any sort of sophisticated linear algebra machinery, because I haven't found one that's really nice. So I don't know why this is actually a useful fact, but it's true, and we can prove it's true using the Jordan form. And I think what is important about this example is it shows that just by understanding what each of these Jordan blocks look like individually, understanding how they behave, sort of like what we did in this step, we're able to get a theorem about matrices in general. So this is the general idea of how we're going to attack this classification theorem for finite simple groups. What we're going to start by doing is identify the correct sort of building blocks for finite groups. And then we're going to figure out a way to try to build up to general groups. So if we want to classify all finite groups, which is like the ultimate goal of finite group theory, we best find a way to build up out of the simple building blocks, and we better understand the simple building blocks. Okay, so let's go over here. So we're going to write down our program to classify all finite groups. So step one, this will be find correct find the correct building blocks. Step two is going to be understand these building blocks. Okay, and step three, we want to build complicated structures from simple ones. Okay, so this is like our three-step program, and the rest of the talk will be dedicated to sort of going through this step by step. Unfortunately, we can't actually complete this this third step. We can do step one, step two, step three. If we could do it, we'd be done with group theory entirely. It's at this point sort of completely out of reach to solve this problem, but we'll try. So let's try to identify the correct building blocks for finite groups. And so I'm going to give this definition for what a simple group is, but I think it's not so obvious that this is actually the correct definition sort of a priori. So I'm going to do some work to try to motivate why it's the correct notion of these building blocks. You might think, well, our simple groups should be maybe groups that are just like their order is a single prime power or something like that. And you might think, well, okay, we know by the fundamental theorem of arithmetic, all groups will have an order that's the product of a bunch of prime powers. And maybe if we understand these p groups, where p groups will be groups of order p to the n for some prime, maybe we can understand those and just like sort of string everything together, right? And there's other ways you might think to define the notion of a simple group. We're going to define it sort of based on the internal structure of the group itself. So simple groups, we'll say G is simple if and only if there are exactly two normal subgroups. Of G. Okay, so this is just the definition. And for those of you who haven't taken a group theory course, perhaps, what are these normal subgroups? Well, these are sort of the correct subgroups to take quotients by. So in linear algebra, you learn, okay, you have a vector space, you have a subspace, you can quotient out by the subspace. For groups, it's not nearly as nice. If I give you a group and a subgroup, I can't give like a well-defined structure to the quotient in any sort of meaningful sense, unless that group is normal. So these are the correct things to take quotients by, and they also have lots of other nice properties that make them sort of the most interesting subgroups to consider. I'm also saying that there are exactly two normal subgroups. So the trivial group is not considered to be simple, just for sort of like some technical reasons and not having to deal with sort of trivial cases. And another thing is that the trivial subgroup is always normal in the entire group, and so is the entire group. So a group always has at least two normal subgroups. And so I'm saying a simple group is one that has the minimal number of normal subgroups without being trivial itself. And so this is good. We have a definition for simple, but it's not immediately obvious in any sense how we would actually build up finite groups from such groups. We might think that we've given a condition that is too strong, and we've picked out things that are too simple to actually build up what we want to build up. So for example, if we took our Jordan blocks not to be what they are, but we took them to be like diagonal matrices or like scalar multiples of the identity, that's too simple. We can only get diagonal matrices out of that, and there's plenty of matrices that are non-diagonalizable. So let's do a little bit of work and try to show that this is a good definition for a simple group. So our saving grace is going to be the so-called Jordan-Holder theorem. Jordan-Holder theorem. And what this says is let G be a finite group. Then there exists a so-called composition series for G. So there exists some series of this form, so a sequence of subgroups that are each normal in the next one. This triangle symbol means normal. And so we're saying we have some sequence G0 up through Gn, such that G sub I is normal in G sub I plus 1. And we require an additional condition, which is that G sub I plus 1 mod G sub I, which I'm going to define to be equal to C sub I. This is simple in the sense that I described with this definition here. So this is the first part. This is an existence part. The fact that this exists is sort of just like an elementary group theory argument. Either G is simple itself, or it's not simple, it has a normal subgroup, and then we just basically proceed by induction, find a composition series. This is called a composition series, by the way. Find a composition series for the normal subgroup, find a composition series for G mod the normal subgroup, and then there's something called the correspondence theorem, which lets us basically pull everything back through the quotient, and we end up with some nice composition series like this. So this first part is relatively easy. The uniqueness part that I'm going to state now is a little more involved to prove, and I'll omit a proof. Uniqueness. Let's say we have two such composition series for a given group. So we have one that's just these same as before, and now I'll just differentiate between these by adding primes to the second series. Okay, let's say we have two such composition series like this. I'm going to call the composition factors these quotients, these simple groups that arise from this composition series. So I'll call those corresponding to this composition series just C sub I, and then C sub I prime for these guys. And what we have by this uniqueness result is basically there exists some sigma in Sn. Sn is the permutation group on an object, so this is just some permutation, such that C sub I is isomorphic to C sub sigma I prime. And so this is just saying that, okay, I have all my composition factors for the group here, and I have all my composition factors for the group here as well. And I'm saying if I rearrange the order in which they appear, I can get this rearrangement to correspond up to isomorphism. So if we consider the set of all composition factors, whether we take it with this series or this series, that set or multiset will always be the same. Okay? Any questions so far? Yeah.
So there's something that the length of the series having to be unique, I guess.
Yeah, that's right.
Part of the statement.
I should have mentioned that. We can sort of from the start, we take this to be M. The length is not guaranteed to be the same, but yeah, you're exactly right. The equal length, I was kind of implicitly assuming that is a consequence of the theorem, which isn't immediately obvious.
Right. Okay. Yeah.
Anything else? Any other questions? Okay, good. So we have this this Jordan-Holder series, and this gives us some idea why these finite simple groups will be good building blocks, right? Because we can sort of approach the group in question. We can approach this group in question, and we have these simple groups that are arising as these quotients. And these quotients should be getting, maybe they don't have to be getting bigger, but they're sort of getting closer to the group in that they're living in these groups whose size is getting closer and closer to G. We might think, and this sort of ends up being a fantasy, it's not true, that if two groups have the same composition series, then they'll be isomorphic. And if this was true, this would be wonderful, and we would essentially be done with finite group theory again. So maybe it wouldn't be so wonderful because the subject would be too easy. But let me give a quick counterexample to why this fails, and it fails sort of hugely. It's not even close to being true. So if we have a composition series for Z mod PZ squared, this is just like the cyclic group of prime order. So it's like the integers modulo P, right? We have this composition series, and our first composition factor is, of course, just Z mod P. And then here, it's also just Z mod P, right? And now I'm going to give you another group, and it's going to have the same composition series as this one. So we'll take this first term to be Z mod P as well, and then the group will actually be Z mod P squared, okay? And it's easy to check that the composition factors are just going to be Z mod PZ in both cases. Again, this first one is just sort of you just quotient out by something appearing in a product. And then the second one is maybe not so obvious, but there's something called Lagrange's theorem. If we take a group of order P squared and quotient by something of order P, we're going to get a group of order P. Cauchy's theorem tells us that all groups of prime order are cyclic, and so we know it has to be isomorphic to Z mod PZ again, right? But of course, these two groups are definitely not isomorphic, right? This guy's a cyclic group, this guy's a product of two cyclic groups, definitely not cyclic. Product of two finite cyclic groups is only cyclic when the order of those groups is coprime. P is not coprime to itself, so we don't get this isomorphism. So the Jordan-Holder theorem, as nice as it is, doesn't solve this problem entirely, and we're going to need something more sophisticated, and this will be the notion of a group extension. And I'll just touch on this briefly because it's sort of outside the scope of this, but hopefully this will conclude the motivation for our choice of the simple group. So group extension. So if I have a short exact sequence of this form, we say that G is an extension of n by q. Okay, so short exact sequence, this is something you see in like a group theory course or like a topology course or something. If we have some such short exact sequence, then we give this definition of extension. Some authors will actually switch the order of n and q. Some will say it's an extension of q by n, but that's never really made sense to me. So I'll call it n by q. And what we now see, and this is sort of the culmination of our efforts to motivate this notion of a simple group, we'll see that if you give me some group to start with, I can find a Jordan-Holder series for it, a composition series, and I can construct a short exact sequence of this form. Okay, short exact sequence, this is not clear, let me write this again. This is the short exact sequence in question. And basically what we do is we take the group appearing in this composition series, let's say of length n, and we take the group directly preceding G, we mod out by it. So this will be the projection map, and then we can just include this group here. Yeah, question?
You can do a quotient equals gn minus 1 as a. Or
Oh yeah, here,
Well, it's normal, right? Which is the same thing.
yeah, I mean, it is a, sure, any normal subgroup is a kernel of a homomorphism, right? But in the Jordan-Holder series, we have that each is normal in the next.
okay.
Let's say you don't like the Jordan-Holder series, you can also find, in any finite group, you can always find a maximal normal subgroup. And this is just because, or yeah, you can always find a normal, what am I saying? You can always find some maximal subgroup and then, or a maximal normal subgroup. And if you quotient by that, you'll get something simple as well, just by like the correspondence theorem. And so even if you don't like the Jordan-Holder series, you can take something like that and take a maximal normal subgroup, and that will guarantee, just like with the Jordan-Holder series, that this will be simple here. So what we now have with this terminology is that G is an extension of G sub n minus 1 by G mod G sub n minus 1. And this guy is a simple group because it arises from this Jordan-Holder series. So we see that G is an extension of G sub n minus 1 by a simple group. And likewise, G sub n minus 1 will be an extension of G sub n minus 2 by a simple group. Continue going on down the line, and we see that any group will arise as a finite sequence of extensions by finite simple groups, just extending each of the groups that appear in the Jordan-Holder series. Yeah, question?
Yeah, so if I say G is an extension of n by q, and I give you some q, like I give you some simple q, let's say, and n is some random group.
Yeah.
Some random finite group, let's say. It's not solved to like classify all G's that you could get.
Yeah, this is what's called the extension problem,
Right.
the group extension problem. Extremely hard problem, and we basically have no idea how to do it. Or if we were able to do it, because we know how to classify finite simple groups,
Right.
if we could understand what all the possible extensions were, I could just say, okay, here's my proposed classification, right? I know what everything looks like when I extend by a simple group. And so I can say what this group and what this simple group look like sort of by our induction hypothesis,
Right.
and then just verify that what comes out of that also obeys the classification. And we would sort of be done.
If both factors are normal, like if I say G is an extension of n by q and both n and q are are simple, is there a solution to the extension problem there?
I'm not positive, but I think no,
Okay.
but I'd have to check on that. I'm pretty sure, no, we don't have a solution to that either.
Okay.
But I'm not positive. Any other questions? Okay, cool. So hopefully this has motivated for you why we should care about these finite simple groups, because any group will arise as some finite sequence of extensions by finite simple groups. And sort of, if we could solve the extension problem, then we would solve all of finite group theory. So let's try to now understand this classification theorem that I've been hinting at this whole time and actually state it. Of course, there will be no proof because the proof is something like 10,000 pages long across hundreds of journal articles. So no proof today. Okay, so let's do this classification theorem, or I'll abbreviate things. For the rest of the talk, I'll just write CFSG for classification of finite simple groups. And what we have, the result is any finite simple group is isomorphic to exactly one member of the following collection. What is this collection? Well, we have cyclic groups of prime order. We have A sub n for n greater than or equal to 5. We have groups of Lie type, and we have 26 sporadic groups. Okay, so this is the statement of the theorem, right? It's really nice. We have 4 different families that any finite simple group can belong to. But there's a lot of stuff going on here. First of all, verifying that the cyclic groups of prime order are simple. That's sort of something you do in a first course on group theory. And these are the only abelian simple groups, also just by the fact that we have this thing called Lagrange's theorem. And then for abelian groups, we have a converse to Lagrange's theorem. So these are the only abelian finite simple groups. These A sub n groups, this is the alternating groups. So before I mentioned the symmetric group on n elements, which is all the permutations on n objects, the alternating group A sub n is all of the even permutations on n objects. So it's all of the permutations that can be obtained as an even number of swaps of elements, otherwise known as transpositions. And it's not easy at all to even show that A sub n for n greater than or equal to 5 is simple. So maybe in a first course on group theory, you'll show A sub n for n equal to 5 is simple, but for the higher cases, it's not immediately clear why that's the case. These Lie type groups, also very complicated. There's 16 different infinite families of these. So this is sort of far too varied for me to spend any time going into detail. That's a topic for a different time. And then we have 26 sporadic groups. So these are groups that don't fall into any of these other very broad categories. If you've heard of the monster group, that's one of the sporadic groups. And 20 of the 26 sporadic groups arise as subquotients of the monster group. And then there's just like 6 other ones that are not known to be related. So this is the setup. And let's try to make some progress toward a proof of this. Yeah, question?
So why are they called Lie type?
I'm not exactly sure.
Okay.
I don't know really anything about the Lie type groups, unfortunately.
Presumably because he came up with it, so it's named after him.
I was meaning like, is there a relationship to like Lie groups?
Well, he was just working on groups, all like groups.
Yeah, that's a good guess. A lot of the work with these groups is like modular representation theory. So you're working with like representations over like FP or something and trying to understand that. And if you look at like the Wikipedia page for the classification, there's all these different like breaking down the Lie type groups by their rank and these different characteristics you can or not different, I guess these different ranks you can consider and whatnot.
Okay.
Yeah. And then the sporadic groups, these are also not so well understood either. So, okay, let's try to make some progress on how we prove this. So we have a couple 2 main ideas. what are our main ideas? First, we want to prove all non-abelian finite simple groups have even order. Okay, wonderful. And then we're going to use the so-called Brauer-Fowler theorem to study centralizers of involutions. Okay, so these are the two steps. So let me talk about how these are connected. Well, first of all, the abelian finite simple groups are known just to be these cyclic groups of prime order. So we already understand the abelian case for finite simple groups. And so we're only left with the non-abelian case. So the non-abelian case is the hard case of studying these finite simple groups. And what this theorem here gives us, it gives us a guarantee that they will always be of even order. And the reason why this is so important is our second step, we're going to study centralizers of involutions. So if I give you a group G and you give me some element, we call this an involution, provided it has order exactly 2. And by Lagrange's theorem, we know that the order of any element in a group divides the order of the group. And so even order groups are the only groups that can have these involutions. So before we proceed with this characterization using involutions, we best guarantee that we're only going to be working with groups of even order. Okay? Questions so far? Okay, so yeah, not going to give a proof of this first theorem either. This is called the Feit-Thompson theorem. Feit-Thompson. And this was sort of the catalyst for the whole project to classify finite simple groups. Before we proved this Feit-Thompson theorem, we didn't really think that it was within reach. We didn't have any strategy to really proceed. And in order to prove this theorem, basically you need to go to grad school for math, take your graduate math courses, then you need to read maybe like 3 or so specialized books on character theory of finite groups and finite group theory. And then after you've done that, you might be able to prove this theorem. So extremely difficult theorem that probably only a handful of people in the world have actually gone through the whole thing, but it was proved back in the 60s. And so we do have this result. And the next result is this Brauer-Fowler theorem. And this I will be able to give a full proof of, sort of assuming some lemmas that involve more technical machinery. So one more note, what is a centralizer? A centralizer of an element in a group is just all of the elements that commute with that element. Okay, so what we're going to do is we're going to take these even order groups, we're going to find order 2 elements, and then we're going to look at all the elements that commute with order 2 elements, and this should give us some good information about the structure of the group. Okay, so before proceeding with the proof, let me actually state precisely what this Brauer-Fowler theorem states. So this states that there are finitely many finite simple groups with a centralizer of involution of order n. Okay, so this is the statement of our theorem. Basically, it tells us that we can give, well, we can't necessarily give a list, but in principle, if we could give a list for what these finitely many groups look like, it would be a finite list of all the finite simple groups that could ever have a centralizer of involution of order n. So there's only finitely many, so sort of in principle, we might be able to actually give a list of what these guys look like. So we get this guarantee of even order by the Feit-Thompson theorem, and now we're going to basically reduce this to there only being finitely many simple groups with a certain property, and then look to study centralizers of involution to conclude. Yeah.
So if we have a group of even order, it can have multiple involutions, right?
Yeah.
So it can have multiple central, like you can have centralizers of involutions of different order, right?
Yeah, yeah.
So like, when we think of, like, there's no good way to say if I have a finite simple group, what its quote unquote centralizer of involution is, right?
Yeah, we could definitely, yeah, there should definitely be different order of these.
Right, okay,
Yeah, because we know any two involutions,
right,
or if we take if we conjugate in
Right.
involution, we're gonna get back to another
right,
involution.
yeah, yeah,
And so the centralizer of conjugate involutions should have the same order.
right,
But there do exist groups in which we have non-conjugate involutions.
right,
And in the case that we have non-conjugate involutions, we should have by like orbit stabilizer or whatever.
yeah,
we-
yeah,
Yeah, I'm not entirely positive, but I would imagine if you have non-conjugate involutions, it's possible for their conjugacy classes to be of different sizes, and that would give different sizes of involutions. So there's some flexibility here. I guess it's kind of like pick your favorite involution,
right,
and it has a certain order.
Right.
If we can find one with a centralizer of involution of a very small order, we're gonna get a tighter bound on how many finite simple groups it could be.
ah,
And so, that's probably the best
Okay.
choice. So we'll see in the theorem, we get a bound in terms of n, actually.
okay, awesome.
Yeah, any other questions? Okay, let's prove the theorem. So first I'll state two lemmas. You want to prove the lemmas, take a course on representation theory and a course on group theory, and you'll see how to prove the lemmas, or just be very skilled and clever with combinatorics, and you might be able to prove one of them without much machinery. So, oh, okay, this talk is pretty good. So, lemma. This lemma arises from studying the symmetric and alternating powers of representations and understanding their characters, and then you decompose a function that tells you the number of square roots a certain element in a group can have in terms of its irreducible characters in something called the Frobenius-Schur indicator. And basically, by doing this Frobenius-Schur indicator computation and this decomposition, like in terms of the orthogonality relations for characters, we get a bound on the number of involutions in terms of this like class function decomposition, and then sort of standard combinatorial arguments will give this lemma. So this first lemma is pretty tricky, and then the second one's a lot easier. So let order of G be even, then there exists some non-trivial element, so some x not equal to 1 in G, such that the index of the centralizer in G of x is less than or equal to alpha squared. I haven't told you what alpha is yet, so alpha is going to be the order of G minus 1 over T. I haven't told you what T is yet, and T is equal to the number of involutions in G. So we get this strange bound. Note that the index of the centralizer of an element is just the size of its conjugacy class by like the orbit stabilizer lemma. And so this is saying something about the size of conjugacy classes of involutions is related to the size of the group and the number of involutions. And unfortunately, I don't have a great motivation for why this results. It comes out of this this study of the symmetric and alternating powers. The second lemma is easier. So let G be a finite simple group, no longer required to have even order. Let H be a proper subgroup. Proper subgroup with index in G being equal to n. Then this implies that G embeds into A sub n. So I give a finite simple group, you give me some proper subgroup of proper subgroup of this finite index n, then G is isomorphic to a subgroup of A sub n, right? We also require H really to be a proper subgroup, because if like H was the entire group, we can't always embed a group in A sub one. Not every group is trivial, right? So this is the statement of this theorem. This guy is a lot more obvious. Basically, you just consider the action of G on its collection of cosets, and then G is a finite simple group, so that map has to have a trivial kernel, right? And then basically you just argue about some stuff involving the order. Basically, A sub n is normal in S sub n, so the preimage under a homomorphism of a normal subgroup is also going to be normal. And so we know the inverse image of A sub n has to either be 1 or the entire group. And we basically show that it can't be 1, so it has to be the entire group, meaning G maps into A sub n, and it does so injectively. And so this is basically how the proof of this fact proceeds. Questions so far? Okay, cool. We have our two lemmas together, and now we can prove the Brauer-Fowler theorem. And then with this Brauer-Fowler theorem, we can give sort of the first attempt of a proof that was actually given by like Richard Brauer himself. This was sort of his idea. So let's do the proof. So let G be a finite simple group with tau in involution, and the size of the centralizer of tau equal to n, right? So the this Brauer-Fowler theorem here, we want to show there's finitely many finite simple groups with a centralizer of involution of order n, and we're saying let G be one of these. And we want to show there's finitely many possibilities for G, and that will allow us to conclude. Okay, so the first thing to note is we have this relationship. The size of this index is just the order of G over n. This is just Lagrange's theorem. So this is simple. We have this equality here. And what we have is that this is going to be less than or equal to T, where T is once more the total number of involutions in this group. Okay, and why is this true? Well, as I was saying to Yash earlier, if we take the conjugate of any involution, we will again get an involution. So this is the size of the conjugacy class of tau. Tau is an involution. All its conjugates are involutions. So we have at least this number of involutions. Okay. So what do we do now? We use, where is it? We use this lemma here. Let's call this lemma 1, and this is lemma 2. So we use lemma 1 to by lemma 1, we can guarantee the existence of some x, which is non-trivial and which satisfies this property. Of course, we have that this index has size greater than 1, because this centralizer cannot be the entire group. Otherwise, x would be in the center. But we know that this group is a finite simple group, so it has non-trivial center. So we get that this greater than 1, and then the less than or equal to alpha squared just comes from the tricky lemma. But what we can now note is alpha squared, by definition, is just order of G minus 1 over T squared. And this is less than order of G over T squared, right? We have a smaller numerator here, bigger numerator here, so we get this strict inequality, right? So this is great. And now we have this bound here, order of G over N is less than or equal to T. So this tells us that this guy here is actually less than or equal to N squared, right? We just multiply by N, divide by T, and this gives us less than or equal to N squared. And now things are starting to look a little bit like the setup of lemma 2 here, right? We have this centralizer now. It's a proper subgroup, right? Because it has this index greater than 1, and it's certainly non-trivial. And we know that its index is less than or equal to n squared, but actually because we have this less than here, it's actually strictly less than n squared. And so what we know is this index is less than or equal to n squared minus 1. And therefore, we get that G embeds into a sub n squared minus 1. Okay, because this index is going to be some number less than or equal to n squared minus 1. And if we have like a sub m and a sub n, where m is less than or equal to n, we can always just embed a smaller alternating group in the bigger one. So that's how we get this guy. And perhaps, you know, we can get something even better if we know more about the structure of the group if we want. So sort of back to what we discussed before, here's our bound in terms of n, and n is the size of the centralizer. So we sort of want these small centralizers of involution. So this is the Brauer-Fowler argument. And so let's give sort of one explicit attempt to prove, yeah.
So so the finite limiting options that you would maybe have to consider are all the like proper subgroups of A sub whatever, right?
Yeah, exactly.
But it's not necessarily true that you can take any subgroup of an alternating group and find a group, like you can't go backwards.
Yeah, because there's going to be subgroups of an alternating group that aren't finite simple.
Right, yeah.
Because actually, just like we can embed any group into Sn, we can also embed any group into An as well.
Right, yeah.
So yeah, too much to ask for
Yeah,
to go
Okay,
backward.
yeah, that makes sense.
Any other questions? Okay, now let's do proof of classification of finite simple groups, or our attempt. We can't actually do the proof. So let's see, what do we want to do here? Yeah. So we're going to suppose the classification for finite simple groups. Suppose this fails, okay? Let G be a minimal counterexample. To the classification of finite simple groups. Okay, G is a minimal counterexample. So what we can note now is that G is non-abelian. And this is just because we already know what the abelian finite simple groups look like, and they obey the classification. So one that doesn't obey the classification certainly has to be non-abelian. And now this is where we use FT for Feit-Thompson. This implies that the order of G is even. Okay, so we know G is non-abelian. We know all non-abelian finite simple groups have even order. So we get this implication. And now it's like, okay, group of even order, what do we do? Well, we have this nice Brauer-Fowler result, which lets us deal with this case. So what we can do is let tau be an involution. Perfect. And what we can do is we can observe that the size of the centralizer of tau, so centralizer in G of tau, this is going to be strictly less than the order of the group, right? And this is sort of another standard argument. Well, the centralizer can't be the entire group, otherwise we have something in the center. And this is a non-trivial element because it has order 2. Simple groups can't have a non-trivial center, right? So we get this bound. And what this tells us in particular is if we consider some Jordan-Holder series for this centralizer, all of the composition factors and all of the groups appearing in that will also have order strictly less than the order of G, okay? Because G is a minimal counterexample to this theorem, we can apply the classification for finite simple groups in its full strength to all of the composition factors of this centralizer, okay? And here's where things sort of start to break down. We're in a good place, but the next 2 tasks prove to be very difficult. With the full strength of this classification result, sort of in principle, we should be able to classify what this centralizer of tau can look like up to isomorphism. So, yeah.
Sorry, why is the centralizer simple?
Yeah, so the centralizer is not simple. This is why this is, or it could be, but we don't know it is. So the reason why this is sort of in principle is the idea is that we take a composition series for this guy. Each of its composition factors are simple. We apply the classification to those, and sort of like you were mentioning earlier, well, if we can solve like some sort of a less complicated version of the extension problem, then maybe we can say what this centralizer looks like.
And this is something that's done, so like if you take a centralizer of an involution and we can like do the extension problem in reverse for that. Sort of.
We would hope to be able to do
Okay.
that. So sort of both of these things I'm going to say are in principle because we haven't actually figured out how to do them, and the real proof proceeds in a slightly more general way. But I do have two theorems that show that this strategy is not unreasonable, where there are cases where we actually can do this for certain cases.
Okay.
So we have this guy. We want to classify what this centralizer looks like up to isomorphism. Maybe there's 10, maybe there's 100, maybe there's 500 different isomorphism classes for this guy, but we should be able to list them out. And if we can do that, then by the Brauer-Fowler theorem, for each such isomorphism class of this involution, we know that there will be finitely many finite simple groups that could correspond to that. So we have this this bound in terms of the order of a centralizer, and we can sort of strengthen this to say, okay, let's find all of the finite simple groups that not only have the same order as this centralizer, but actually themselves have a centralizer of involution isomorphic to the one that we've given here. So then we would basically apply Brauer-Fowler, and we would try to say, for all of the different possibilities for the centralizer up to isomorphism, here are all of the possible finite simple groups that we could have with a centralizer of involution isomorphic to CG of tau. And then we would just need to show, okay, all of these possibilities actually obey our classification for finite simple groups. And that would be a contradiction to G being a counterexample, because G, of course, has a centralizer of involution isomorphic to this guy. It has it up to equality, right? So in this way, we would get a contradiction and we can conclude the theorem, and that would be great. Okay, so any questions so far? I have two more quick things to say, and then that'll be it. Questions?
So
Yeah.
just to clarify, this strategy is not actually what works in the general case, or at least not for all of the cases in the more general.
Yeah, not for all of it, but it does play a big role
Okay.
in the proof. So this wasn't sort of all for naught. It ends up being extremely useful, but instead of taking centralizers of involutions, we actually want to take normalizers of P groups. And I'll sort of explain the connection here in a second. And that's the proper generalization that's used to complete the proof. It's called these normalizers of silo subgroups are called local subgroups, like P local subgroups. And there's a book called like Local Analysis. And this is one of the sort of building up to the Feit-Thompson theorem. We want to do this local analysis, which is the study of these normalizers. And that's sort of how we get Feit-Thompson and other classical results. Okay, so now I'll put some of this on the board to be, let's go over here. To be, so first I'm going to state two theorems without proof, which are sort of theorems that tell us what we're doing is not so unreasonable. Okay. So let G be a finite simple group with tau and involution. Again, just like we've been doing. Now we have two theorems. So if the centralizer in G of tau is isomorphic to D8. So this is the dihedral group of 8 elements. So this is like all the possible rotations and reflections on like a square or like a cycle of length 4. So it's, yeah, what is D8? It's all the graph automorphisms of a cycle of length 4, if you want like a formal definition. And then we have this great guarantee. We have that G is either isomorphic to A6 or G is isomorphic to PSL 3,2. So this is our first theorem. And then our second one is even better. If CG tau is isomorphic to V, where V is the Klein 4 group, so Z mod 2 squared, then we know exactly what G is. G is A5. Okay, so these are 2 theorems that tell us that the approach is not entirely unreasonable, because we're saying, okay, if we know what these centralizers look like, we can say exactly what a group that has such centralizer has to look like. And that's exactly what we are doing over here. We just have a lot more cases. So, right, there would be a whole bunch of different possibilities for what this centralizer has to look like. But for example, in these 2 cases, if we had a centralizer that was D8 or this Klein 4 group, then we've sort of completed it. So in order to sort of finish this program, we would have to go through a whole bunch more cases and say, okay, if we know what the centralizers look like, here's a list of the groups that they can be. And just for, a sanity check, these guys actually obey the classification, right? So any questions? Yeah.
I guess I'm still not seeing like why we get finite, like, I guess our classification, is indexed over n, where n is the order of the centralizer of involution. But like for each n, we would still have to calculate all the different possibilities. Right? I guess I'm still not seeing how we reduced like a finite number of families or like.
So you're saying, so if I have a centralizer of involution of order n,
Right.
then there's,
Finitely many options for my group.
yeah.
But for like, how do we, but it seems like we know for every single n what the possibilities are, right? Or like,
What do you mean? How do we know the possibilities?
like, is that not what the big theorem of classification tells us? Like, you can always,
Well, yeah, I mean, once we know the classification theorem, then we can recover all this information about the centralizers. But this is prior to having the classification,
right?
right?
Okay,
So yeah, the classification theorem in full is a lot stronger than what we're doing here. But even there's a post on Math Overflow about this, about do we have a full list of all the centralizers and everything? And basically people were saying, yeah, we probably do based on the classification, but no one like actually has it listed out.
like, I guess my question is, so then like, if with the full classification theorem, if it's, I guess I'm trying to understand, if I have a group, the
Yeah.
classification theorem exists, is it, I guess, practical to like do some calculations with the group, let's say like calculate the order of the centralizer of involutions or this normalizer of p groups, and then match it to one of these examples? Like, can I actually use
Can
the
I actually do
classification
this?
theorem? Yeah.
Well, sort of based on the fact that we haven't been able to do it, we might think, no, this is not actually something that's reasonable to do. But our guarantee of like the finiteness is something that people, at least at the time, thought was, okay, this is a possible strategy. So when people were actually doing this, this was like back in the 50s, right? The classification was completed in full in 2004, and we were essentially done with it in 1983. So sort of 30 years later, we were able to complete everything. But prior to that, we didn't really know what was gonna work and what wouldn't. But when people see theorems like this and they have this sort of reasoning, you're thinking, wow, this seems pretty simple. Let me just find all the possibilities and classify them, and maybe we'll be done like that.
But like, my question is like today, with the full strength of the theorem, let's say I'm working with some group and I want to match it to its isomorphism class with the class. Like if I have a finite simple group and I want to match it to its isomorphism class by this classification theorem, can I do that? Like, is it practical, or is it more just like theoretically you could? Like if I have a computer, like if I can calculate all the stuff that I need to calculate, like normalizers of P groups and whatnot.
Yeah, I mean, I think for small enough groups, it's almost certainly possible just by like our computer systems.
Okay.
For you give me an arbitrary finite simple group, how you guarantee that it's finite simple without it like being one of these is maybe the question I would ask.
Okay.
Because it's like, maybe the question is asked backward where like, because for you to tell me, okay, this is a finite simple group, well, you would have to justify that somehow. And that
Right.
justification is sort of telling us
Right,
what it
okay,
is.
I see what you mean, yeah. That
Yeah.
makes sense. Yeah.
Okay, so, okay, one final note, and this will be on the local analysis thing. So what's going on here? We've been studying CG of tau, and recall order of tau is equal to 2. This is actually equal to the normalizer in G of the cyclic subgroup generated by tau. So what we have here is this is a normalizer of a 2 group. Right? Sort of our simplest 2 group, the 2 group that actually just has 2 elements, right? But we see that what we've been doing this whole time is a special case of normalizers of 2 groups, and we can extend to normalizers of P groups. And the reason why we might think that we should extend to normalizers of P groups is we have tons of these so-called P complement theorems, guaranteeing the existence of a so-called, normal P complement. One such theorem, which is the simplest one, which is not actually so simple, but this is called Burnside's transfer theorem. And this says, I won't write it out, but if you give me a silo subgroup and it is contained in the center of its own normalizer, then I can find a normal P complement to that silo subgroup. So I can find, basically, we start with P. P is contained in the center of the normalizer of P. This implies there exists some N normal in G such that the index of N is equal to the order of P. And this is one such theorem, and we have many more of these P complement theorems, which let us understand such groups as the semi-direct product of a silo subgroup in this normal complement. And so using the strength of these theorems and trying to understand these normalizers is sort of closer to the real direction of the classification. Yeah.
Is the normalizer of a P group not the same as the centralizer of one of its generators?
Which generators? Like,
Because the P group is cyclic, right?
no, a P group is just a group of order like P to the N.
Oh, it's not an order P, it's order P to the N. Okay,
Yeah.
Sorry.
Yeah.
That makes a lot more sense then, yes.
So what you were saying, I probably is true.
Yeah.
maybe.
Yeah, but that makes a lot more sense. You're saying power. It can also be the order can be a power of a
So if you look at like, for example, the number of isomorphism classes of a given 2 group, they grow extremely fast as we increase the power on 2. So if you take like 2 to the 10th or something, or like 2 to the 20th, and you want to say, okay, how many isomorphism classes do we have? Is going to be some gigantic number. So these are complicated groups.
Yes, that makes sense.
All right, any other questions? Okay, that's it. Thank you.